Physical Sciences, Lesson 17. Topic: Electron interactions, multiple bonds, oxidation state, molecular shape and conduction. Turn to Lessons 17 and 18 in the Learner's Workbook. Integration. This lesson integrates with life sciences, molecular biology, mathematics. Molecular shapes relate to any work in geometry involving shape. Prior knowledge, grade 11, lessons 15 and 16. Lesson overview. In this lesson, you will discover the behavior of electrons in solids like metals. Learn about an interesting and important category of materials that lies between metals and non-metals called semiconductors.
Hello South Africa and welcome to the Physical Sciences classroom once more. My name is Tinyiko Kosa.
And I'm Peter Glover.
Yes, and today in this lesson we're going to revise and apply some of the things we did in our previous lesson. And I want to say that even in the upcoming lesson after this one, there will be more things around what we will be talking about today.
We're looking at applications of all of this good stuff we're learning about electrons and that kind of thing.
Exactly, and to start with, we're going to look at the theory of Lewis theory of showing electrons. Now, what Lewis did was to say, let's only show electrons that are on the outermost layer of the atom. In other words, valence electrons.
Okay, so we're going to look at valence electrons. Why don't we take a look and you just talk us through it and I'll draw some pictures. Okay, Taniko, here we have our periodic table and we are showing the first 18 elements. You talk us through it and I'll draw these pictures.
Now with Lewis diagrams, what we do is to show the valence electrons by means of dots or crosses around the symbol of an atom. Now let's start with hydrogen, for example. The symbol is H and hydrogen is in group 1. It has got only one valence electron, so only one cross there or a dot can be used to show that electron. Okay. Now let's move on.
Let's take this one
perhaps to lithium. Lithium in group 1, element number 3, it is in group 1. It has got only one valence electron, so it is similar to hydrogen.
Okay, and we see, of course, that even though it has many more electrons, not many more, it's number 3, so it's got 3 electrons, but we're ignoring these 2 that sit very close in, close to the nucleus, and we're just showing the outer electron.
Exactly, and actually what Lewis is saying is that the symbol of the element would be showing us the core electrons. In other words, all the core electrons are represented by the symbol, and all we do is to show the valence electrons.
So it's the nucleus and those inner electrons that which are being shown there, however many there are.
Exactly.
And so for sodium we'd also have 1
because it's in group 1. Now also see that there is a relationship between the group number in which an atom is found and the number of valence electrons around that particular atom. We are looking at group 1 and you can see that all we have is just 1 electron as a valence electron for those atoms.
And so presumably for beryllium we would show 1.
Yes, beryllium is in group 2, so we would have 2 of them.
Okay, 2 of them. Now, do I show them together?
No, we're not going to show them together, particularly because these valence electrons can be involved in bonding. So any valence electron can be involved in bonding irrespective of where it is in an orbital. So for that reason, we will spread them out.
Okay. And magnesium, just for the record, let's show it in the same way.
Exactly.
Good. Now we're going to move on.
Now let's take, for example, boron. Boron is in group 3, and therefore we expect to have 3 valence electrons for boron. So it will be B, and that B represents all the core electrons, and the valence electrons are shown by the crosses as Peter is drawing them there.
Okay.
Moving on to carbon. Carbon is in group 4, sorry. So we expect to have 4 valence electrons. Now check carefully at what Peter did. All those 4 electrons have been spread evenly around the carbon atom.
And that's as far as we can go
That's
with singles.
Exactly. Now, let's check what is going to happen when we come to group 5 elements. Let's take nitrogen.
Okay, here we go. These are getting a bit close together. I don't want to confuse them. So here I'm going to start using dots.
Yes.
For no other reason than I don't want to be confused.
We are in no way saying that nitrogen is bonding with carbon at that moment.
Yeah.
All we are doing is to show the valence electrons.
Okay.
Now, it's 5 valence electrons. So we've got 4 there.
4, 5.
So the 5th one now begin to pair up with another. Now, moving on, let's go to group 6. And
Oxygen.
let's take oxygen.
I better draw it a little smaller, and I'll use crosses again.
Yeah.
1,
So
2,
6 valence
3,
electrons for carbon.
4, 5, 6. And the fact that I chose to pair up these two opposite one another has no significance again.
No.
Okay.
No, not at all.
7.
Group 7, and we're now talking about a very special group of elements as well. Let's look at fluorine. There is fluorine. We should have 7 valence electrons, so 5, 6, 7.
3 pairs and this one unpaired electron.
Yes.
Okay, and we'll see the significance of that again later.
Yeah.
Okay.
Now, we know very well that with the noble gases, we would have all those 4 electrons paired up there. So we feel that it's not necessary for us to go into that point for now, but all we are saying is that because the valence electrons will all be paired, the noble gases do not have that much affinity for electrons, and therefore they are not that reactive.
Right, they don't bond.
They don't bond.
In fact, it was just a few years ago that somebody got the Nobel Prize for chemistry for showing that in fact you can
get them to bond,
but under very special circumstances.
Exactly.
Okay.
Exactly.
Great. Now, where are we going from here? There's the Lewis diagrams, and how do we use these things?
One thing I want to emphasize again is that we drew these valence electrons like that because we are saying any one of those electrons can be involved in bonding. And we are also going to use these valence electrons to show how the molecules get their shapes. In other words, molecular shapes. Why do we have shapes like that?